Assalamualaikum warahmatullahi taala wabarakatuh. Okay, right, today I'm going to give a little bit lecture on chapter 5, collection and analysis of rate data. The objectives of this chapter is basically for you to determine the reaction order and specific reaction rate. This lecture is divided into two, which is analysis of data to find rate law. Basically, we have two methods that we like to look, which is differential method of analysis as well as integral method. And in lecture 2, we will concentrate on analysis of data to find rate law using other methods such as method of initial rates, half-lives, and as well you look into differential reactors. There are normally two types of reactor that we use to obtain rate data, which is basically to obtain K as well as to obtain the reaction order. The first one is batch reactor. So it's basically you have a reactor and then you put in your reactant and then you wait until specific time and then you stop your reaction and basically you record your data such as the concentration of A. Okay, and then what you have to do is you run another sample, but now the time is become T2 and then you will record your CA2, for example. And similarly, you run again and then you got the third data at T3 and then your concentration at CA3, and you can do so on and so on. The next one we're going to look into the differential reactor. Okay. Differential reactor is different compared to batch reactor because differential reactor is a type of flow reactor. Okay, flow. And the flow reactor, it is a continuous flow where basically the reactants comes in here, react here, and then you will get whatever left out, the reactant which is not converted here. And in the middle here, normally you are putting your catalyst. You have to put your catalyst as thin as possible, okay, so that this particular section it react as a CSTR. Because what does it mean by CSTR? The point of reaction is here, the concentration of FA, A for example at this point, and the concentration of A at this particular point, or A at this particular point, or A at this particular point is the same. Okay, so if let's say the concentration are all the same, then it meets the requirement for a differential reactor. There were several methods that we can use to analyze the rate data. There are differential method, there are integral method, as well as some other methods. We are not going to address these two methods, but you can read further from Fogler's book. Okay. And in differential method, they have several types of analytical method, which is you can use graphical method, finite difference method, as well as polynomial method. In integral method, it's just a try and error. So basically, you like to guess different type of order, then you plot a different type of graph. Okay. In order for you to make an analysis of data to find the rate law, initially you must consider the following reactions. For example, like A goes to product, or A goes to B, and everything. And then you know that in a batch reactor, the mole balance is given as follows by a rate law. For the analysis of data to find rate law, so we have to look into the rate law given, which is in generic, it is in alpha term. And then for a batch reactor, the volume doesn't change. So in terms of stoichiometry, V equals to V naught. And if you combine all of this together, then basically you will get this particular form. And if you look at this particular form, in order for you to make it as a natural log, okay, so that you will get in terms of the form of y equals mx plus c. So if let's say you plot a straight line of ln dCA by dt versus ln CA, okay, it will give this, right? So this is ln dCA by dt versus ln CA, and your slope is alpha, and your intersection is ln K, so which you can calculate afterwards. But now is the concern is how to get your dCA by dt. If you look at this particular example, right, and then we like to look into differential method analysis. Okay, it's given that the following reaction takes place in an isothermal constant volume batch reaction system. So you know straight away that this is delta T equals to 0 and delta V equals to 0. Okay, the initial concentration of B is given as 0.5. The concentration of A at different time was recorded as shown in table 1. Determine reaction order with respect to A. So you are required to know because the reaction rate is given as CA alpha. Okay, so you are required CA alpha, CB beta. Okay, so you are required to determine your alpha with respect to A. And then if we assume that the reaction order with respect to B is first order, determine the specific reaction rate constant of the reaction, given that this is the particular reaction. So now you were given that at different time, 10, 50, 100, 150 with different CA value. Okay. You can use two methods again, which is differential method as well as but now we're going to look into graphical method as well as in terms of differential method is divided into two. One is it's supposed to be divided into three, which is another one is polynomial. So we will look into the graphical method as a work in class, and finite difference method. In order for you to calculate your dCA by dt, okay, there are several formula that you can use, right? So which we also will address this in the class. I will address about this graphical method in the class afterwards. And if you look at the integral method, okay, just now we were talking about differential method, now we're talking about integral method. We need to guess the reaction order and integrate the differential form of equation used to model the reactor use. So if the right reaction order is assumed or guessed, the plot of the concentration versus time data should be linear. Three examples we consider, which is 0, first and second order. So if let's say you guess, initially you guess from a set of data, okay, you got your T and you got your CA, right, T from 0 up to certain value, T10 for example, CA from CA naught until CA10 for example. So if let's say you guess straight away this is a zero order. So if let's say it is a zero order, you have to plot a graph of CA versus T straight away. And if let's say you got a straight line, okay, then you can straight away assume this is zero order. Okay, because the straight line, the equation is as follows. It will give as follows. So if you got a straight line, straight away you will know that it is a zero order. And the intersection here is your CA node. And then the slope here is basically your rate constant. For first order reaction, okay, so the difference is that you have to plot this particular graph where the y-axis is ln CA naught over CA versus T. Okay, so initially you have this table again, T CA naught, sorry, CA, and then you have to plot a graph of ln CA naught over CA. So at T equals to 0, CA is equals to CA naught. Okay, so you should get this one as 0 because CA naught equals divided by CA naught is 1, ln 1 is equals to 0. So you got this particular point. And then you keep continue until T equals to certain numbers. Okay, and then until you got your CA up to that certain numbers, and then finally you can calculate this value, and then you keep plotting here. And then if let's say you got a straight line, then basically this is guessed as first order. So from there you can calculate, get your K value, which is your rate constant. For second order, so this is the reaction order with respect to second order. If you rearrange back this equation, then basically in order for you to get a straight line, you will get this integration form. Okay, so what you have to do is basically, again from the table, this is T, CA, and instead of ln you have 1 over CA. So again, calculate T equals to 0, CA equals to certain values, CA equals to CA naught, so you should get here the value of 1 over CA naught. At T equals to 10 or T equals to X, then basically you can have your CAX, and then this is 1 over CAX. Okay, so basically you plot the table again, and if let's say you got a straight line, then this is your slope K, and then you can say straight away this is a second order reaction. We're going to do the similar things again, okay, with the differential method that using the example given earlier, so we can compare between the two methods, which is differential and integral method. Okay, I'm going to stop up till here, and then we'll continue for the second lecture afterwards. Thank you very much.